we've got a car. I'm in a car. I'm driving, and I'm traveling at a constant rate of 60 miles an hour. So I'm got my cruise control set or something. So I'm going 60 miles an hour. There's 60 miles an hour. There's t equals 1, t equals 2. I'm driving straight along at that exact same rate. Okay. There's the function that represents this. True? Do you all agree with that?
Yeah.
Yeah.
Now, here's the important question. Now, think real hard about this. How far did the car go? How far did I go in those 2 hours? Tough one.
120 miles.
Are you sure?
My intuition would tell me yes.
All right. Yeah, good. 120 miles, right? Pretty straightforward. Everybody good with that? I hope.
Yeah.
Yeah.
All right, cool. All right, now, okay, we're gonna make things a little bit more complicated here. Okay, here I am going 60 miles an hour. Watch me go. Look at that, I did it. I went 60 miles an hour for 1 hour, and then instantaneously, because my car is magic or something, I instantaneously increased my velocity to 70 miles an hour, and my function now looks like this until I get to t equals 2, and I went exactly 70 miles an hour for those at second hour. Pretend those are straight lines going across there. How far did I travel during these 2 hours?
130.
130 miles.
Are you guys sure?
Yeah.
Oh, good, okay. 60 plus 70, right? 60 in the first hour, 70 in the second hour. Easy, right? Should be easy.
Yeah.
Are we getting
All
into
right.
integrals here? Is this our introduction to integrals? Or are we doing more derivative stuff first?
Oh, no, we're done with derivatives now.
Okay, sweet.
Yeah. I mean, not that we're done with them. We're still going to use them, but. All right. Here's t equals 1. Here's t equals 2. It's getting even more complicated now. Oh, that didn't even come close to connecting. I don't like that either. That's better. Look at that. I started at exactly 60 miles an hour, and somehow over the course of those 2 hours, I increased my speed at a constant rate so that when I finished, I exactly hit 70 miles an hour at exactly 2 hours. Those don't really line up very well, do they? That looks better now. Now that's 2 hours. Okay, how far did I go this time?
I want to say 130 miles again.
You want to say 130 miles, or you are saying 130 miles?
I'm going to guess 130.
Wow.
The 125.
Any other guesses? I got a 130, I got a 125. What was my average speed?
65.
65. My average was 65, right? If I increased it at exactly constant rate, my average speed was 65 miles an hour, and 65 miles an hour for two hours ought to be 130 miles, right? Do you all agree with that?
Yeah.
Okay.
Yeah.
And it's right, 130 miles. That's if I could somehow in a perfect world with no traffic, if I can, and somehow I was able to have a constant increase in my speed. If I could do this, it's exactly how far I would go. Everybody good so far? Easy, right? All right. Now my car is traveling at a variable rate. I started off at 60 miles an hour and I finished at, I don't even know how fast. And I sped up, and then it looks like maybe I went about the same for a little, and I went a lot slower because there was traffic. I was like driving through LA or something. And then I got like annoyed and like sped up and drove on the shoulder of the road for a while or something. get around the traffic. How far did my car go?
Is the area under the curve?
I don't know, is it? Did that work over here? How far did I go? I went 120 miles in this first situation, right?
Yeah.
And if I were to find the area of this lovely little rectangle here, it's a rectangle that's 60 by 2, right? 60 times 2 is 120. What about this one? 60 times 1 and 70 times 1. It's the area underneath this function that I drew. Same thing here. Oh, that was not anywhere close to the 2, right? What's the area of this? This is a trapezoid, isn't it? It's got a base 1 of 60 plus a base 2 of 70 divided by 2 times the height of that trapezoid. Came out to be 130. Yep, and that's exactly what it is. Every time you want to know how far you went, if you have a time velocity graph, the total distance that you traveled is just the area underneath that curve. And we'll find that there are a lot of uses for finding the area underneath a curve, right? If I could find this area right here, that would be the distance that I traveled. Now, it's not so easy to find that area, is it? Because one, I don't know how high up this function actually went. I don't know how low down this function actually went. I certainly don't have a good way to find an area of this curve thing here, right? Any way that we could sort of come up with an area underneath that curve? Maybe a good way to approximate it? Any ideas on that?
Draw rectangles under the curve.
Draw rectangles under the curve. Oh, man. All right. Here I go. I'm going to draw some rectangles. How do those look?
Yes, like that.
They look fantastic.
I mean, that's what you guys told me to do, right? There we go. I've drawn some rectangles. Good or no?
How about drawing rectangles that match the numbers we know?
That match
it'd be
the
like-
numbers we know. I know
like-
all numbers.
Well, we know 60. So you
That's
can
true, we
start
do know
with a
60.
point at 60, and then you can go over to where 1 is, but that extends a little bit outside the curve.
Oh, but that goes outside. Oh, that goes outside the curve.
Yeah, that's not good.
That's not good. Oh, man. All right. Yeah, I'm not sure who it was that said draw some rectangles, and then I, gave that snarky little picture of a bunch of rectangles. Whoever said that, who said that? Who said draw rectangles?
Jacob.
Jacob. Okay, yes, you were right. I should be drawing rectangles. I just shouldn't draw them like I did. So we can approximate this area by drawing little rectangles, and there's a couple different ways to do it. And one is called the left rectangular approximation method. And we're going to talk about all these different methods today. And today we're going to talk about how to approximate areas underneath curves, because it's a very important concept in calculus. So what we want to do as we're driving along for these 2 hours is, let's say every 15 minutes, check in with what our exact speed was. So at 0, t equals 0, we were going 60 miles an hour. So we're going to draw, with any luck, a little rectangle there. Okay? And find the area of that rectangle. Well, if we knew exactly how fast we were going at t equals 0, we should know that this was 15 minutes or a quarter of an hour times 60. And we should know that we went a quarter of 60 miles or 15 miles in that first 15 minutes, right? Approximately. Then we'd go to the value of the function because we took this data point as we were driving, and we could find this next rectangle. And my rectangles are going to look really bad because I'm drawing on the laptop screen. Then we went to this next checkpoint here, and we drew another rectangle. And we'll note, oh, man, that's terrible too. We'll note that some of these rectangles, as I do this going across here, starting at the left endpoint of each interval, what do we see? That some of these leave off little sections, right? Like I missed this little section right here, right? But I also added in a little bit extra on some of these other sections where I went over, right? And some of those will, they'll sort of cancel out a little bit with each other. We're not going to get an exact answer, but that green that's under and that yellow that's over is at least going to get us sort of close to the exact area underneath this curve. Is it going to be perfect?
No.
No, it's not going to be perfect, but it's going to be okay, right? It's going to be a decent approximation. What could we do if we wanted to make this approximation better?
Draw more
Make
rectangles.
smaller rectangles.
Yeah, make more narrow rectangles, right? Instead of taking a data point every 15 minutes, I could take a data point every 10 minutes and I'd have 6 rectangles for each hour, right? Or I could take one every minute and I could draw 60 rectangles in here. And I wouldn't be able to draw them because I suck at drawing. But if I had 60 little rectangles in there, the little bits that we were under or over would become much smaller and smaller. And that's going to be our goal, is to be able to get as many little rectangles underneath this curve as we can. Okay. So you guys sort of see what the general idea of what we're going to do here is, at least for this left rectangular approximation. We're going to take the left endpoint of each little subinterval. We're going to call each of these subintervals. Right, we're going to start at the left endpoint of each one, draw a rectangle, and then the left endpoint of this one, wherever it hits the function, draw another one. Left endpoint of this one, where it hits the function, draw another one. And then, since we know all those data points, we just sum together the areas of each of the rectangles and get an approximation. Good or no?
Good.
All right.
Good.
Now, we could also do this with a right endpoint of each subinterval. Should look about the same. So I would just start at the right-hand side and say, oh, that was terrible. I wouldn't say it was terrible. I would say, let's draw a rectangle. Let's pretend that's a good-looking rectangle. It's not, but we'll pretend it is. And we just do this from the right endpoint of each of my subintervals. And we'll note again, we've got some pieces that are over and we've got some pieces that are under. True? But some of those will cancel out. And again, if we were to make more rectangles, we should get a more accurate representation. What do we notice about, let's go back to this last one. What do we notice when our function is increasing, then the left rectangular approximation is doing what? It's a little bit under what it should be, isn't it? Anytime our function is increasing, we're leaving off pieces.
Yeah.
Yeah.
But we'll note that anytime f is increasing, a left rectangular approximation is an underestimate. And this is an important point that you'll want to remember, okay? And anytime that f is decreasing, our left rectangular approximation method is an overestimate. And if you don't remember it, I mean, you could pretty quickly draw the picture and see that that's the case. Everybody good there?
Yeah.
And what about for the right rectangular approximation method? Anytime our function is increasing, then the right rectangular approximation is an overestimate. And anytime f is decreasing, our right rectangular approximation is an underestimate. Good or no?
Good.
All right. So how else could we draw rectangles underneath here? Using these little subintervals that we've got. Rather than start at the left end point and make a rectangle, or start at the right end point and make a rectangle, where else could we start on our interval?
The middle?
The middle. We could do a midpoint rectangular approximation. That's exactly right. So we'd start here at the midpoint, say that's about the midpoint, and we'd draw a rectangle. And we'd go to this midpoint and we'd draw a rectangle. And this midpoint and draw a rectangle. And this midpoint and draw a rectangle. And we'd notice that we've got a little piece that's over and a little piece that's under for pretty much all of those, don't we? But the little pieces that are under and over are, I would think, a lot smaller than what they were in the left and the right approximations. Would you agree?
Yeah.
Yeah, and this should be a better approximation. But unfortunately, whether the function is increasing or decreasing doesn't tell us whether it's an under and overestimate, which is why sometimes it's nice to have these other ones to know, all right, if I know that my function is only increasing and I use the left one, then I know I'm going to be a little under what it should be. Or if my function is always increasing and I use the right one, I know my answer that I get is going to be a little over what it should be. Well, for this one, we know it's going to be a little more accurate, but we don't know if it's going to necessarily be more or less than the exact value. Right? So it's got, they've all got their own uses, but it's just important to understand the differences between them and what the function's nature can tell you about each one's approximation. Everybody good?
Yeah.
All right. So what we're going to do is we're going to take a nice simple function, f of x equals x squared. And we're going to do the interval from 0 to 3. And we're going to try to approximate it using a left, a right, and a midpoint rectangular approximation and see what we get for each one. Sound good? Should be, I think, pretty easy. We'll start with the left. So if we start with the left, and in fact, what I'm going to do here, I'm going to put a couple more of these in here so I can do each one separately on the graph. So if I do the left rectangular approximation method first, my interval is from 0 to 3. I should start at 0. And if it says I need to have 3 subintervals, then those subintervals will be 0 to 1, 1 to 2, and 2 to 3. Everybody agree with that?
Yeah.
Okay. So the left endpoint at x equals 0 is 0. So this one actually has a height of 0, which means that rectangle doesn't even really exist. And we're missing out on a bunch of this area. What about the second one? Second one, that rectangle ought to have a height of 1 squared because at x equals 1, the function's value is 1 squared. And we're looking at this rectangle. And then the last one should be 2 squared. Should look about like that. Hey, that rectangle is finally pretty good. Good or no?
Good.
Yep.
Spectacular. All right. So the height of the first rectangle was 0 times the length of that rectangle, which was 1. Then the height of the second rectangle was 1 times its length, which was also 1. And then plus the height of the last one was 4. And that one had a length of 1 also. What do we end up with as our approximation?
5.
5, right?
5.
And we know because this is a function that is increasing, and we used a left rectangular approximation, and we can see visually here that we're missing quite a bit, right? Missing all of this. We know it's an underestimate. Everybody good with that?
Yeah.
Okay. Now, let's do a right approximation. So, same criteria, interval from 0 to 3, 3 subintervals, so 0 to 1, 1 to 2, and 2 to 3. Our first rectangle will be up all the way at the function's value at x equals 3, which is
9.
9. Hey, that was a pretty good rectangle for how tall it was supposed to be. Then the next one, the function's value at x equals 2 is 4. So we'll have this rectangle, and then at x equals 1, we'll have this rectangle. Everybody good with that?
Yeah.
Hopefully so. All right. So our first rectangle that we did was 9 height with 1 width. Second one was 4 height and 1 width, and the last one was 1 height and 1 width, which gave us 14. And we know, once again, that since this function is increasing, the right rectangular approximation will give us an overestimate. Good or no?
Good.
Good.
All right, let's do the midpoint then. So, same criteria, 0 to 1, 1 to 2, 2 to 3. What's the midpoint from 0 to 1? Ought to be x equals
0.5.
Yep,
0.5.
0.5, 1/2. So we've got that rectangle. Then we should have the midpoint between 1 and 2, which is 3/2, which will be up right about there. And then we ought to have between 2 and 3, which is right there. And we have those 3 rectangles. So what's the height of the first one? It ought to be 1/2 squared, right? Times the width. The second one ought to be 3/2 squared times the width. And the last one ought to be 5/2 squared times the width. Everybody good with that?
Yeah.
Cool. So this gives us 1/4 plus 9/4 plus 25/4, which equals what? 35/4?
Yeah.
35/4 is what? 8 3/4? Yeah. So we end up with 8
Yeah.
3/4. Anybody know what the actual area underneath this curve is?
Nope.
No. I'll let you know that the actual area, which is very easy to find once we learn how to do our integrals, the actual area is actually 9. And so we ended up just with 3 subintervals from 0 to 3. So intervals of 1 unit length, and using a midpoint approximation, we ended up at 8 3/4 rather than 9. We were awfully close. Okay. So pretty decent approximation, really, when you think about it. Maybe not as good as some of those square roots that we did with the linearization, but you could imagine if instead of using 3 subintervals from 0 to 3, what if I used, what if I had a calculator to do it for me with a program, put into it, and I had 100 subintervals here? Well, we could probably get pretty darn close to the actual value of 9, don't you think?
Yeah.
Yeah.
Any questions on how to find these left, right, and midpoint rectangular approximations?
Are we going to
How
need
would
to
you-
know this like after we learn the correct mathematical way, or is this just going to become like obsolete afterwards?
No, you will still need to know it because, and in fact, you will almost certainly be tested on it on the AP test, because what they like to do sometimes is give you just a set of data points and say, all right, approximate the area underneath this curve just from a set of data points where there's no function for you to actually take an integral of, which is what we're getting towards. Or they may just give you a graph where you can see data points, but you don't know what the function itself is. So you do need to know it, and you do need to know those under and over approximation things about it also.
Okay.
Yeah, they always ask every year on the AP test. There'll be at least one or two where it's an approximation method, and then they'll ask you if it's an under or an overestimate. So.
I must have missed it. Where's the 1/2 and the 1 coming from? Like,
So the 1/2 is the midpoint of the first subinterval. So we had 3 subintervals, right? For each. So let me go back a second. For each of these ones that we did, we had the subintervals from 0 to 1, 1 to 2, and 2 to 3. Good with that? Yep. Okay. So, so for this one, they all have these 1s in them, right? Those 1s are the lengths of these subintervals. So from 0 to 1 is 1 unit, from 1 to 2 is 1 unit, and from 2 to 3 is 1 unit, right? And then the heights were all, for this one, it was 0, squared was 0. This one was 1 squared was 1, and this one was 2 squared was 4, coming from the value of the function itself. And so we did the same thing here. This one was, they all had widths of 1 still, but this one was 3 squared, 2 squared, and 1 squared. Well, this one, we took the midpoints of those intervals. So the midpoint of 0 to 1 is 1/2. So the height of our function at 1/2 was 1/2 squared, right? Because it's x squared. And then 3/2 squared, and then 5/2 squared. And then the 1s are still just the lengths of those subintervals.
got it.
Yeah, good.
Well,
Good.
will this always be the case where like left is always an underestimate and right is always an overestimate?
Remember that the left is an underestimate if the function is increasing, but it's an overestimate if the function is decreasing, right? So if the function is increasing, which ours was underestimate, if the function is decreasing, it should be an overestimate. Same with the right, right? If it's increasing, it's over. If it's decreasing, it's under. So if, instead of asking you from 0 to 3, I had said -3 to 0, then our function would be decreasing. And when we did our left approximation, it would be an overestimate. Does that make sense?
Yeah.
Cool. Any other questions on that, or everybody good?
Good.
All right, so I'm going to give you guys just a minute or two here to see if you can approximate the area underneath this curve, 1 over x plus 1, on the interval from 1 to 9. And so I want you to divide it up into 4 equal subintervals and use a midpoint approximation. Does that make sense what I'm asking you to do?
Yeah.
All right, let's see if you guys can do that. Ready, go. So if we're talking about the subinterval or the interval from 1 to 9, and we want to have 4 subintervals, we ought to have one that goes from 1 to 3, right? One that goes from 3 to 5, one that goes from 5 to 7, and one that goes from 7 to 9. Everybody agree with that?
Yeah.
So our midpoints ought to be 2, 4, 6, and 8. And that ought to be what we use as our midpoints of each of our subintervals for our approximation. So what's the length of each subinterval?
2.
Right, the length of each subinterval is 2. So each time when we figure out what is 1 over x plus 1 for x equals 2, or for 4, or for 6, or for 8, we got to multiply that value by 2. So it's 2 times 1/2 plus 1, and then plus 2 times 1/4 plus 1, and then 2 times 1/6 plus 1, and 2 times 1/8 plus 1. Everybody good with that?
Yeah.
Yeah. And what did that come out to be?
10.08 and then Continuous 3.
10.083.
Yeah.
Okay. And so what is that as a fraction? I like fractions better. Anybody got that as a fraction?
10 and 1 over 12.
What was it? Over 12?
Yeah, 10 and 1 over 12.
10 and 1/12. Okay, so 121/12. Yeah.
Yeah.
Or, well, actually, we could say that's exactly equal to 10.083 repeating. Good or no?
Good.
All right. Anybody know what the actual value of that is?
Nope.
No?
Maybe
It,
10.
Nah, it's not. It's the natural log of 9 plus 8.
What does that come out to be?
I don't know.
Roughly?
You guys tell me. You're the ones with the calculator in front of you. I don't use calculators. I just do all the calculations in my head.
10.19.
10.19. So yeah, it's off by, about 1/10.
0.2 actually.
Pretty decent. What's that?
0.2.
Okay, yeah. About 1/10. Everybody good there or no? No? Yeah?
Good.
What did you guys say? 197 or something like that? Cool. All right. So, real quickly before we keep moving on with some more new stuff here, you guys all familiar with sigma notation, summation notation? This Greek letter here, sigma, capital sigma.
Yep.
You've seen this before or no? Anybody not familiar with this? Want a little bit of an explanation of that?
Yeah, that would be nice.
Okay, so this sigma, this summation notation, just means a sum of. It means sum together these things. So I said sum together all of the A sub k's. All right, so sum together all the A's from the first A, from k equals 1, to the nth A, which would be A sub n. So this summation just means the first A plus the second A plus the third A plus the fourth A plus all the way up to the nth A, right? And the one before it would be the n minus 1. So if I said, what's the sum from k equals 1 to 5 of A sub k, we'd say that's A sub 1 plus A sub 2 plus A sub 3 plus A sub 4 plus A sub 5. Good or no?
Good.
So far? If I said sum together from k equals 1 to 4 of k, what would that be?
4
10,
plus.
Yeah, 4 plus 3 plus 2 plus 1.
Right, starting at
1
k
plus 2
equals
plus 3
1.
plus 4.
Yeah, we'd write it as 1 plus 2 plus 3 plus 4, right? If I said sum together from k equals 1 to 5 k squared, that'd be 1 plus 4 plus 9 plus 16 plus 25, right? That'd be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. Good or no?
Good.
Okay. How familiar are we with these summations and like rules for summations on like, suppose I asked you, let's find out how familiar you are. Suppose I asked you to find this, the sum from k equals 1 to 100 of k. That'd be what? That'd be 1 plus 2 plus 3 plus 99 plus 100, right? You guys know what that is?
Is it 5,050?
It is 5,050, not 5,050. We don't say ands when we're talking about numbers unless it's for a decimal, but that's a different story. Yeah, 5,050. How'd you get that? Do you know? Or did you just, somebody told you that once and now you know it?
Well, there's actually a summation or like thing on your calculator, but I averaged the 1 in 100 and multiplied by 100.
I see. Okay, perfect. Yeah, so there's this old story about a famous mathematician named Gauss, and he was the first one that really came up with and wrote out a strategy for doing this. Theoretically, he did it when he was in like 2nd or 3rd grade or something. His teacher was mad at him because he was smarter than everybody else and the teacher. So what Gauss did was he said, well, this summation is also the same as doing this, doing it backwards, which I think that was you, Alex, that was saying this, or no?
Oh, I don't really, I just set them backwards. I don't really make this connection.
Oh, I thought you were the one that said 5,050.
Oh, I just averaged 1 in 100 and multiplied
Right.
by 100.
Yeah, exactly. That's exactly what Gauss did. He said, well, this is the same as having 2 of these summations, which is 101, right? If I add the first 2 of these together, 1 plus 100 is 101, and 2 plus 99 is 101, and 3 plus 98 is 101, and it'll continue being 101 for all of these. And if I had 100 integers here, how many 101s do I have?
100.
I should have 100 of them, right? So 2 of these summations ought to be 100 101s, right? And so if I just want one summation of it, oops, I don't know, I just wrote a K. It ought to be that, which ends up being 5,050. Yeah, pretty ingenious that like a 2nd grader came up with that. We could write this out as a formula though. So let's, instead of going to a specific number, 100 up here, let's see if we can sum from k equals 1 to n of k. So that should be 1 plus 2 plus 3, and so on, all the way up to, what's the term before n? It's n minus 1, right? And then n. And so we would do the exact same thing. We'd say that this summation could also be equal to n plus n minus 1 plus n minus 2 plus all the way down to 2 plus 1. And when we combine these together, we'd see that each of these terms was an n plus 1 term. And how many of those n plus 1 terms would I have?
Okay.
N
N.
of them, right? And so 2 of these summations ought to equal n times n plus 1, or 1 of these summations ought to equal n times n plus 1 over 2. Everybody good with that? So if I want to sum together the first n integers, it's always however many integers I'm adding together times the next number divided by 2. And this is a formula that we're going to use actually a little bit. We won't get to it today probably, but you're going to want to know it for next time. So make sure you just kind of commit that to memory. It shouldn't be too bad. Right? If you want to sum together the numbers from 1 to 50, it's 50 times 51 divided by 2. You want to sum together the numbers from 1 to a million, it's a million times a million 1 divided by 2. Easy enough?
Yeah.
All right, cool. There's another one that you should also know. I'm just going to write it here. Suppose I wanted to sum together all of the square numbers. Anybody offhand happen to know what that one is? 1 plus 4 plus 9 plus 16 plus 25 plus 36 up to n squared? No? It's n times n plus 1 times 2n plus 1 divided by 6. So I should have circled this whole thing. That's another one that you're going to want to know, and we'll use, let's see, what's tomorrow? Thursday? We'll end up using that tomorrow as well after the quiz. So I'm not going to go through and prove that one. It's a little more complicated, but you should know that the sum of all the integers is n times n plus 1 over 2, and the sum of all the squares is n times n plus 1 times 2n plus 1 over 6. So if I want to know what's, what is the value of 1 squared plus 2 squared plus 3 squared all the way up to 100 squared, it's 100 times 101 times 201 divided by 6. If you try it with the first couple numbers, you'll find that it works out nicely. Right? If I wanted to find the sum of the first 3, right? If n was 3, that would be 3 times 4, which is 12, right? Divided by 6, which is 2, and then 2 times 7 gives you 14. And if you add 1, 4, and 9, you get 14. Should work every time. Any questions or issues with that? All right, cool. Now you're wondering why. Why did we do all this? And I'm going to go to this page right now, and you're going to still look at me and wonder why I'm talking about this. So bear with me. I'm just going to kind of talk about this, and then you can come back and look at the notes online later if you want. I'm not going to write a whole lot here. So what I've got here is some random function. And what I've done with this random function is I've drawn a bunch of subintervals, and we'll note that those subintervals are not necessarily equal subintervals, right? The length from x0 to x1 is different than the length from x1 to x2, right? And so I've drawn some rectangles in them, and I've done that using midpoints. So I found the midpoint of each one, c sub 1, right? And c sub 2, and this one would have one c sub 3. And then I labeled some interval the kth subinterval. And when we talk about the kth subinterval, all I'll be talking about is any random subinterval that we might want to choose between the beginning point of my interval a, or x naught, and the end point of my interval b, or x sub n. So I've just picked some random subinterval, the subinterval x sub k. And what would the area of this rectangle be? Of any arbitrary, randomly chosen rectangle. It should be the height of that rectangle, right? Times the width of that rectangle. It should be the height times the width. Well, what's the height of it? It's the value of the function at that point. And what's the width? The width of it should be just the change in the x value of that kth subinterval, right? Because they're all different, right? Delta x1 is different than delta x2, which is different than delta x3, which is different than delta x4, which is different than delta x5 and delta x6, and so on. Yeah. Everybody agree with that? That would be the area of this rectangle?
Yep.
That area could be positive, right? It might be below the x-axis, where we'll talk about it being a negative, even though the area itself is not negative, but we'll talk about this the value down here being negative, right? It could be 0 if part of it spans, like I might end up, it might not be an exact rectangle. I might have this weird trapezoidal thing in between there. It might be 0. That's okay too. So what our goal is going to be is similar to what we were talking about before when we were doing these approximations, is I want to get the exact area underneath this curve. Well, in order to find that exact area, I need to have what? I need to have more subintervals, don't I? Because what will more subintervals do to the width of each of these rectangles?
Smaller. and
Makes
more
them
accurate.
smaller, right? And more accurate. All right. And so if I could put more and more and more of these together and then sum them all together, then one would hope that I should be able to come up with a pretty good approximation for the area underneath the curve. And so how would we sum together all of the rectangles? What would we have to use? We'd have to use this summation notation, right? We'd want to say, let's take the sum from k equals 1, so from the first rectangle to the nth rectangle of the area of each of these rectangles. Everybody good with that so far?
Yes.
Okay, so that's our goal, is to take the sum. This is the, I'm going to do this in a different color here. This is the sum of, and then this is the, all of this together. This is the area of the rectangles. So that's our goal, is to sum together all of the areas of all the rectangles. Good or no?
Yeah.
Okay, so let's see here. This is what we've got here, right? We call this sum, this summation, a Riemann sum. And that's what this is all about, is Riemann sums. And we talked about the lengths of these subintervals getting smaller and smaller. Well, what would happen is our approximation becomes more accurate as these subintervals get smaller and smaller. And if we could make the largest of all of those subintervals, so I don't know which one of these is the largest of all of these subintervals, doesn't really matter, but if I can make the largest one of them get very, very close to being 0, what would happen to all the rest of them? If they're all shrinking down at the same rate, if the largest one is very, very close to 0, then all the other ones should be also very close to 0, and in fact, even closer to 0 than that largest one. Does that make sense? I know we're getting a little conceptual, and so it's hard for me. I can't see you guys, so I'm hoping that that's all making sense. So the subinterval that we call the largest one, we call it the norm of the partition. Right here, the norm of the partition. And so we write that as this double bar P. And so we want that one to get very close to 0. Well, how can we make that thing very close to 0 without it actually becoming 0? Because if it becomes 0, we have a problem, right? If the length of the largest subinterval is 0, well, we no longer have rectangles. True?
True.
So how do we make it 0 and be able to evaluate it as 0 without it actually being 0?
Limits.
The limit.
Limits.
The limit. So our goal then is going to be, what we want to do is to take the limit as the norm of the partition approaches 0 of this sum from k equals 1 to n of all of these areas of these rectangles. Does that sort of make sense?
So is that the final equation for
Oh gosh,
finding an interval
oh
right
gosh. No, it's not the final equation, but don't worry, we'll be to it in just a moment. Okay. I know we only got like 2 minutes, so we got to get there quick. So this is our goal, is to do this. And I think I got that there. Okay. this is it. So our limit as the norm of the partition approaches 0. The sum from k equals 1 to n of f of c sub k times delta x sub k. We call this thing the integral. And this is called the integral, but it's not the final version that we're going to use, because what would be really convenient is if I didn't have, let's see, 1, 2, 3, 4, 5 different variables equaling a 6th different thing with a function included in it. That's pretty complicated. True?
True.
Yeah.
So
Yeah.
what we're going to do is, instead of having unequal subintervals, we're going to have equal subintervals. Okay? And if I have equal subintervals, I don't have a norm of the partition anymore because they're all the same. And rather than making a specific one of them approach 0, I can just make the number of those equal subintervals approach what value?
0.
No, I want the number of subintervals to be
Infinity.
infinity,
Infinite?
right?
Oh, I see.
And this n is what represents the number of subintervals. So what we're going to do is we're going to turn this into a limit as n approaches infinity of the sum from k equals 1 to n of the heights times the widths. And the widths now don't have to have this sub k on them because we made all of the subintervals equal length. And so now it's just a delta x, and delta x is b minus a over n, where b is the end of the subinterval, a is the beginning of the subinterval, and n is the number of subintervals. And so we're going to look at that as n approaches infinity. And so that's what we're going to end up doing tomorrow. We'll talk a little more about that again, because I know we're sort of out of time here, but that's the gist of what we're doing. Everybody good or no?
Wouldn't delta x just be 0 then if n is infinity?
No, because n's not infinity, and it's approaching infinity. But effectively, yes.
Okay.
Don't worry, you'll see. It's all going to be, it's just going to be lovely. You're just going to love it when we do this tomorrow. It's going to be great. It'll all sort of, I hope, come together. So for today, that's going to be it.